Astrophysics Lounge after the talk. So if you're interested in that, it's just behind the elevators, in the elevator lobby there. Joe's going to tell us about unleashing feedback, the star formation black hole connection. He keeps telling me he wants to get my reactions afterwards because I told him last night I thought star formation was mostly controlled by stellar feedback, but he's going to tell me otherwise. So there you go, Joe.
Thanks. It's a real pleasure to be here in this very active community. And anyway, so my story now is going to be, everyone can hear me, I'm not using the microphone, so is that okay? So feedback, so it's critical in star formation, we all know that. And I'm going to give you two sides of the story, actually. Just try to give you the pros and cons of whether the feedback may be negative or perhaps positive, and the role that these bizarre things, supermassive black holes, may or may not play. And so here, of course, you simply have a montage of the various places where star formation is either occurring now or certainly occurred in the past in enormous quantity. With massive black hole, lurking in here, and somewhat less massive over here, and a vigorous episode of star formation near the center of the galaxy, not too far away, and star cluster there. So all of these are elements, and of course the merging galaxy, igniting lots of star formation over here. All of these are elements, parts of this really complex jigsaw puzzle. But let me just try to start off by asking one very basic question. And so, when we look in the distant universe, we see very vigorously forming star-forming galaxies. And if the star formation rate that we empirically measure, typically from the far infrared luminosity on telescopes, is larger, much larger even than the time-averaged star formation rate, which is mass divided by Hubble time, then we call that a starburst. And so we see these very luminous episode starbursts early on in the universe, far away. We also see quasars, AGN, powered by supermassive black holes, about as far back as we can see the star-forming galaxies. And they even, as I'll make the point of this talk, they even coincide. Many of the regions that we see forming stars have central AGN, and the AGN likewise is surrounded by intensely star-forming galaxies, embedded in them. And so you can ask the question, is this just a coincidence? Or maybe they are co-eval, they somehow reinforce each other and formed at the same time. Maybe perhaps induced by merging of galaxies, which feeds the gas, helping the stars, and then closer in with the black hole. Or does one influence the other? Is the presence of one stimulating the other? Which way does this go? So, frankly, we have no a priori idea, okay? And we're driven by observation to try to make sense of these very simple questions. So let me begin by summarizing what we've learned in the past couple of decades about galaxy formation. And I'm going to give you two different stories, two approaches to galaxy formation. So, and the problem really is that on the galaxy formation scale, and in a cosmological volume, you have to start off with hundreds of megaparsecs and many galaxies to sample a fair range. You're a very long way from the scales you need to approach star formation, which is sub-astronomical unit scales, so parsec, sub-parsec scale. And so one approach, because it's hard to do brute force numerical modeling, is to develop what are called semi-analytical models, which combine empirical rules of star formation and paste them on to larger scale cosmological simulations. Okay, so let me show you one of the recent semi-analytical codes. I'll just illustrate the parameters that go into setting up the rules of star formation. And with this, one can then make predictions. One can normalize this to, by galaxy formation and make predictions of what happened in the past. That's the basic idea. So this is Andrew Benson's code, for example. And these are the model parameters in his code. Each one of these he has to fit. I haven't counted, probably 25 there, and then there's another 25. And so, there's a lot of freedom here. And I would say that the least you can say about this, I don't think it's very predictive, but you can certainly use it to have models of what we see, but how reliable it is in telling you what happened at earlier epochs than we currently probe, I think one has to take this very, very carefully. So the other approach is to apply hydrodynamics and really go for it, to try to, and again, you have this problem that you can't resolve the ultimate scales of star formation. Nevertheless, you put all the unknown physics into what is called the sub-grid level, the little black box, and then you put in your fluid dynamics, your turbulence, maybe magnetic fields if you're brave enough, that's beginning to be done. But in general, you can make these wonderful images. And so here's an example by Phil Hopkins and collaborators of emerging galaxy. When you stare at things like this, it looks so realistic that the observers probably can't tell, the simulation from the real thing. And it's very tempting if you're an observational astronomer to go with this and think, oh, this must be, a very sort of robust representation of emerging galaxy and induced star formation. But is it? Okay, let me again take you back a little while in history. And so this was really the first simulations were really pioneered by Springer and Lars Hernquist. They did a large box of the universe and watched threads, filaments of matter, dark matter with baryons. Baryons drained down, they made rather clumpy-looking objects and then these condensed into galaxies. And so what you want to get out of this, you like to get the history of star formation. This is what they got. Okay, so again, this was 20 years ago. Okay, so in other words, as you adjust the threshold of star formation, the efficiency which is baryons and stars, both of which are empirical numbers, okay, so you can adjust them as you wish, you can get almost anything you want, actually, and the truth is probably this one over here, close to the truth. But you can see one can predict a lot of things. Now you may say, this is 20 years ago, what has happened since? Well, I just picked an example that came out a week ago. So this is state of the art, and you can see, this is the history of star formation. And again, they have many, many different possibilities, and what we call the truth observationally is the dark shaded line. So the problem is that you really have to adjust your efficiencies and thresholds and hope that you've got the physics right. And then, when you put in so much by hand, I think one has to be very careful. That's all I would say in taking this too seriously. It can be a very good guide. You can use this sort of physics to make catalogs, mock catalogs, to help you get more observing time on telescopes. It's good for that. But when you get the data, you'll almost certainly find that you have to go back to your modeling and then retune the models. That seems to be what generally is happening. Okay, so let me now be a little more specific, and I want to talk about two issues. And one very important theoretical need to explain these things is negative feedback. What I mean by that is if I have a certain amount of baryons, self-gravitating, collapsing, fragmenting, and clouding stars, I cannot have that happen on a free fall time at 100% efficiency. I somehow have to make sure that much of this gas is recycled, and on a free fall time scale at least, I don't use much more than 1/4% or 2 of the gas to form stars. Otherwise, in the Milky Way, it's pretty obvious, we have 100 times so much star formation if I turn all that gas into stars. So something is happening. So the Schmidt-Kennicott law is the relation between star formation rate, which is plotted here. It's measured, for example, from alpha emission in disk galaxies, out to quite high redshift in this particular example. And over here is the gas surface density for the disks, divided in this representation. I've chosen one particular case to show you. They divided into the surface density the local free fall time. And so this includes the free fall time, in the sense of the rotation time for these galaxies. But on the same plot, they also chose a set of giant molecular clouds and Milky Way and used those as well. And the interesting thing is that over several decades in star formation rate and in gas surface density, you can have an empirical law describe much of the data. Okay, and the empirical law is the star formation rate goes as gas density over free fall time times some efficiency parameter. And just very, very roughly, you know that in our Milky Way, the gas has to survive, roughly 50 rotation times, order of magnitude. So you guess this number must be of order 0.02 without doing, those back of the envelope thing you can do. And that in fact it's just the normalization of this line. It turns out to be just about 0.02. Okay. So what more can you say? Okay, so supernovae are the most popular culprit, at least in the simulations, for giving you the feedback that globally at least slows down the gas. Not in the individual case of a cloud, it's also massive stars, but maybe they do other things, they drive winds that disrupt the gas. But it's always massive stars of some sort, but on the global scale, what's put into the simulations of these is the kinetic energy from the supernovae, which drives some sort of blast wave, which eventually sweeps up a shell of gas, which then cools down, eventually clouds, snow clouds into the medium, and this momentum then gives you the feedback. So very roughly, if I do, again, automated calculation estimate, I simply take the energy of the supernovae and divide into that, the unit mass I need to make one supernovae of some mass-forming stars, that is the number of, say, stars above 10 solar masses. And then I define a speed at which this energy outflow starts dumping momentum. That's given by cooling, the snow cloud thing, and compare that to the Russell explosion. And remarkably, if I just put in the numbers into this equation, I get of order 2%, which is roughly the normalization of this line. So it tells you that you must be more or less on the right track. And then if you do one level slightly more refined, again still very, very crude, you go to linear theory of cold disks, and you find that for a thin disk, gravitationally under gravitational equilibrium initially, it's gravitationally stable if it gets too cold, and the maximum growth time for the instabilities and the scale that they would develop because of driving into the clouds is of order of the free fall time. And so again, from linear disk theory, you would estimate that there is some unknown efficiency, which must come from nonlinear theory feedback physics, which a priori you have to guess about, but basically was gas and free fall time. And the interesting thing then is that, again, linear theory then gives you essentially this proportional relation, okay? And compounded by all the nonlinear physics, which no doubt has to come in to explain why so much lays on this line. Okay, so that's a very rough way of arguing that density controls the gas, controls star formation. Unfortunately, the truth is a lot more complicated. So here's one example where if you look at this particular galaxy, and our Milky Way is much the same as this in the center, there's some very dense gas in the center, and this is young stars, but you're not essentially not forming stars at all. So what you learn when you look around the universe is that it's not just gas density that comes in, but in this case it's almost certainly the turbulence of the gas, maybe partly induced by the bar in this case, but if you ask one, but we don't even know what the source of general turbulence is, but basically this turbulence of that helps limit the amount of devastation that star formation can do and restricts it. So it makes the whole story rather complicated. Okay, and so how do you incorporate turbulence into star formation theory? Again, this is a source, I would say, that is still completely new territory for much of the theory, at least as described by the numerical simulations. But it's interesting to look at one simple analytic formulation of this, which uses simulations. And in this case, they study the probability distribution function of density clumps, and show that as you turn on self-gravity and what let the instabilities go, you develop this tail, okay, towards a high density of clumps. And then there's a whole study pioneered by these guys, Padua and Nordman, of the effects of turbulence on the Jeans mass, which is the ultimate criteria of star formation. And you can very simply show that the Jeans mass, which involves, if you recall, the sound speed cubed divided by the square root of density, the sound speed, you raise it by the turbulence speed versus the Mach number, and the density after the shock passes through goes to Mach number squared. So you end up with a Mach squared number dependence, and so you get a boost of Jeans mass, which again modifies star formation seriously. If you've got a turbulence, it tends to suppress it. Anyway, so clearly one has to look at the tail of this and put in the turbulence to get somewhere, and this is something that I would say is a sort of state-of-the-art physics that people are still arguing about how to incorporate the simulation. So I'm just giving you just one example of why one shouldn't take the simulations as they are, even though we have pretty pictures at face value. Nevertheless, here is one other issue that is critical for all galaxy star formation work, that is the gas. The raw material is the gas supply. And so we have these remarkable cases where you can study in nearby objects, high resolution, the gas reservoir. So here is one classic example where you see a star-forming galaxy surrounded by a huge reservoir of gas which is not significantly forming stars. And in this case, likewise, a vast reservoir of gas, this is the galaxy, available for keeping the disk cold as it comes in, and unstable and available to make stars. So this reservoir is critical as part of allowing the disks to be unstable and continue to make stars. And the other part of the story, and again, you learn a lot from this by looking at our own Milky Way. And so one fascinating recent discussion of the Milky Way and other nearby gas-rich galaxies, that if you, in our case, you measure the high-velocity clouds, right? You measure gas accretion now, we know the distances. You measure the gas accretion into the Milky Way. And you find that the gas accretion from the clouds that we measure is not enough to maintain star formation. And so what the idea is in this study was that they say, well, there are exploding stars, supernovae, which blow bubbles of hot gas, maybe whole groups of exploding stars, into the halo, which adiabatically cool as they go out, and then they seed some of the hot gas, boost the cooling, and more gas comes down. And this way one can drive an interstellar fountain that maintains star formation in galaxies like our own. So that's one of the many interesting variations that we need to even understand star formation in the Milky Way, let alone distant galaxies. Okay, so that's, I just wanted to show you examples of the complexity of star formation. But let me go on to something that really connects star formation with cosmology in the most direct way. And that is the luminosity function of galaxies. So what I'm going to show you is what the cosmologists give us, which is a mass function, which comes from simulations of pioneered by dark matter, etc., hierarchical structure, development of clumps, as seen from the C fluctuations of the CMB, all of this we think we more or less understand now, versus what we measure as astronomers, which is the luminosity function of galaxies. And so here is the comparison. Okay, and it's really, really discouraging, okay, at first sight. Okay, and so here is the Schechter function, which beautifully describes the luminosity function of galaxies, and you can parameterize it by the point at which this function bends, which is called the Schechter luminosity, which is this number, and is fairly universal, and you can even study this now far away in the universe, and of course you find that this slope can vary as you go back, etc. But nevertheless, it's a convergent function, and that this means at both ends, this means there is a typical luminosity of galaxies, which is this number. Now, and this is measured, so you can't adjust this red curve. Now, the theory gives you the red curve. You can't just do it. The theory gives you the red curve, which is the mass function obtained from the simplest Schechter, linear theory modification of fluctuations. You compute the fraction which goes nonlinear, and this is what comes out. So, and it's very discouraging at first because you have this huge divergence at both ends, right? There are far more small things and far too many big things. Now, in physics, we can always renormalize. We're allowed that as a bit of freedom. So we can renormalize the mass function. Okay, so let's renormalize the mass function, and we can get it to match at one point. Okay, so this is great. Therefore, there is an inferred ratio of mass to light. What is it? Okay, here's how you calculate what that mass to light is from first principles. Okay, in order for gas to make stars, a necessary condition was cool down. So I simply compare the cooling time for the gas in a halo, and it can be in clumps, or it doesn't matter, it's at a very low temperature basically. And so that can be kinetic energy of clumps colliding, or the uniform, it doesn't matter. With the free fall time, which the other time's going to drop. I simply take the ratio of two time scales. So if I rewrite that ratio, which is the function of the cooling function of the gas, it turns out that we express the mass of the baryons that can cool within a free fall time, and that ratio is here as a free parameter. And all of this is just the physics of the cooling function, which turns out to be a Bode unity in the range of interest. You obtain a mass which just involves the fine structure constant, And this function, which is the gravitational fine structure constant, alpha g is the ratio of the force between the gravitational force in the area of protons and the kinetic repulsion force. And as you may recall, the Chandrasekhar mass, the Eddington mass, can be expressed as simple factors times alpha g minus 3 half. So that's a whole other story, but it's fundamental to the balance between electric directions and gravity. And it turns out to be important for galaxies too. The scaling is slightly different. And the amazing thing is that this number, if I put in this number, it gives me now a mass, okay, which turns out to be 10 to the 12 solar masses. So from fundamental, very elementary physics, necessary condition for cooling, we now have a ratio of mass to observed light, which is a order of 30, which is exactly what we measured. Okay, for typical mass luminosity ratio, it's massive for individual galaxies, massive for very top galaxies. So that's great. Okay, so we've sort of have a simple understanding of one point. Then, for the rest of the story, this is what we do. We put in feedback. Okay, and again, I've schematically called the feedback exploding stars here. It can be a little more complicated, but this is probably the major source. And the idea is that the small galaxies have rather shallow gravitational potential wells, low escape velocities, and so it doesn't take that many supernovae to blow the gas out and leave very pale relics behind that have little gas left to make few stars. And at the massive end, this cannot do the job. The potential was simply too deep for stars to do much effect, and so we appeal to massive black holes, which form at the same time, maybe even before the stars around them, because this is the dense part of the runaway potential well as gas cools, and their output eventually will blow the stuff away, maybe limit things. Let me show you why we think that this, the simplest possible level, is pointing at the right solution. And I'm going to begin with this and then spend most of my time on this. But let me begin with the low end. So here is the evidence. This theory was around long before the following observations were made. Okay, and those observations were to go to the Sloan Sky Survey and make this amazing discovery that by cutting the survey in appropriate colors, so you could look at giant stars as tracers of mass, they picked up, led by the group in Cambridge, these low surface brightness star piles, incredibly low surface brightness galaxies. So we're talking about magnitude of what, -5, -4, all the way down here, whereas the magnetic clouds are over here at -15. So things that are vastly, each is in fact 100 in luminosity, so vastly dimmer than the magnetic clouds. And the numbers of them are consistent with one of the simplest possible feedback models. Okay? And these, you could say, are predicted relics that this disruption feedback theory would expect you to have. Now, there are a lot of details that have not been filled in just after this initial discovery, and the worst of them is, and you can see it clearly on this figure, that if this were the correct explanation for the low surface white force, you have a huge problem with imaginary clouds, which do not fit on this at all. There are two of them. That's one of the people that build statistics and wave their hands. But it turns out this really is a problem in detail. There are issues, but apart from the detail of maybe there are some galaxies that predict by estimation that shouldn't be there at all, or maybe there are too many. But the fact that there are too many small ones can probably be explained by this feedback effect. And there is a prediction that we've now seen for the relics. Okay, so let me stop there for the low mass end, and now turn on to the massive end. Okay, so here the story is that, if you remember the curve I showed you, there were just too much mass in the big galaxies. Stuff just keeps on accreting, all that gas is coming in, building the galaxies up, and we simply do not see that. There's a very sharp cutoff in the Schechter luminosity function. Where does it come from? And the answer is feedback, negative feedback, and the idea is that AGN quench star formation. Okay? So do we believe this? Should we believe this? Well, we have one or two examples. Sadly, they're not, I can't make this a very general argument. Here's the poster child, feedback. It's on a larger scale. This is the Perseus cluster, and there's no question that this AGN in the middle is erupting and driving outflows, radio outflows, and you can see some of the relics of this in these X-ray maps, which is preventing the gas from giving far too high a star formation rate in the central galaxy. You can reduce that inflow this way. And here is an example recently published of something similar happening on the scale of an individual galaxy. This is a giant elliptical, and you can see in this Chandra map If you look carefully at this, you find all sorts of weird features. It's hard to see at this contrast. When you subtract off the uniform component, the smooth part, you find all these various features left behind. And here is the VLA map of the radio outflow, the jet, etc. And there is the idea is that you're looking at the effects of feedback in limiting and in allowing this object, which is a red, a giant red galaxy, to stay red and not be too contaminated by stuff. So this is the sort of thing that negative feedback can do. When we talk about high redshift in a moment, you'll see there's little evidence, direct evidence for it, but it is believed to be the solution to our problems. But there is another way of convincing ourselves that this must come in, and that's this rather simple, again, back-of-the-envelope argument. So I like to give back-of-the-envelope arguments. I think if you can't do those, then you shouldn't believe anything about the story. So at least if you can do it at this level, then things might work. And so this is the back-of-the-envelope. Here we have our black hole, which is growing, accretion disk around it, and eventually it's a quasar-like phase. And meanwhile, the rest of the galaxy is forming. So if this outflow, if the black hole is massive enough, the outflow is strong enough, then the momentum in the outflow will blow the gas out. Okay, so there's a critical limiting mass. How do you estimate what that might be? Well, again, back of the envelope, I take the Eddington luminosity, which is just the balance between, Thomson scattering and gravity light. It's literally luminosity was starting to a black hole, which just goes linearly with the black hole mass, and I compare that with the self-gravity of the region of the gas, the cloud of gas where the stars are forming. That's GM squared over R squared in this case. And when I simply equate these things and just put in numbers, you can translate, you get black hole mass from Eddington luminosity, and this G m over R gives me a sigma squared. Sigma's the velocity exposure of the spheroid. And I get this relation. And the numbers just come from proton mass, Thomson cross-section, etc. So there's no magic in getting these numbers. So this is the claim. Roughly this should happen. You can, depending on whether you consider momentum or energy, this could be a power of 4 or 5. Theory is not that specific, but you get blowout if the black hole is massive and this thing should saturate. What do you actually see? This is what you see. And so this is the observational story over some very wide range in black hole masses, from 1 million solar masses, a couple of million, the Milky Ways here at 3 or 4 million solar masses, up to these giants. M87 is up here at 7 or 8 billion, and then we have things like up to 10. You find this relationship which goes roughly as expected from this simple momentum balance argument. Okay, now all the physics and the dispersion of these points, obviously there are points that might be above the line or below the line, so the details that really have yet to be understood thoroughly, but it does suggest that feedback is helping to understand the fundamental correlation between the mass of the black hole and the potential well the black hole lives in, which generally speaking is the bulge in an early type galaxy, but can also be the bulge of a disk-like galaxy. And one of the whole issues is when you look at galaxies without any bulges, we even in some cases see black holes too, but so things do get complicated. Okay? Nevertheless, ignoring the details, let me show you now what simulations can do. So here's a case of a cloud sitting in a region that not too far away from where an outflow is going to occur, and what you expect will happen is simply that this cloud will be shredded and destroyed, and that's more or less how negative feedback works. And these are examples of simulations by Johan Dwight using a 3D code called Ramses, state-of-the-art hydro simulations, showing you what happens when you have only supernova feedback and when you put in AGN feedback. So with only supernova feedback, there's lots of gas that makes its way into the center, making stars, etc. But with only AGN effect, there's a trickle of gas that will feed the black hole, but one suppresses much of the star formation. So that is the plan. Okay, it seems entirely reasonable that something like this should be happening. I think that massive outflows would destroy the gas, heat the gas one way or another, except, as I said, the direct evidence is limited. So, and you can ask the question, I showed you an example of a cloud being disrupted. Suppose the cloud was more massive enough, so it wouldn't be disrupted. If the cloud was massive enough, then this shock wave, and I'll show you how it emerges in a second, the center, coming from the AGN, would overwhelm the cloud and compress it. So it could enhance star formation. So this leads to the possibility that you might have triggered star formation. So why do we think this might happen? Well, the first statement is that surveys of galaxies at redshift 2 in the infrared show these incredibly clumpy galaxies. This is a star formation rate versus stellar mass diagram. Just designed to show you the range of morphologies over a range of star face rates and masses. And you notice that typically there are 2 or 3 small numbers of incredibly massive gas clumps forming stars. And so if there really are massive clumps out there, and suppose AGN were to go off in these systems, possibly by clumps falling in or feeding the central black hole, etc., what would happen? Okay, so let me now tell you a little bit about the theoretical implications of, and then I will discuss observations for the most part that you can judge for yourself whether they support this idea or don't support this idea. Okay, well, so the first comment is this, that if I take this simple empirical claim that star formation rate, common gas mass at 3 4 times, there's all this magic that goes on in this efficiency parameter, and you can rewrite this in terms of the pressure. Okay, so basically, another way to view star formation rate is gas mass to the square root of pressure. If I replace the thermal pressure in this way of looking at it by the pressure that might be in a radio cocoon driven by an outflow jet from the central source, then I could get an enhanced pressure. Okay, and suppose I get some greatly enhanced pressure, that would have the effect of perhaps of speeding up star formation. So that's basically what can happen. Now, all of this is truly complicated because you have to resolve these clouds and really do the physics properly. The only thing that's been done to date is a very simple linear theory calculation. Okay? And I'll just show you the results of that. You take a gas disk, okay, and it's self-gravitating, vertically stratified, rotating, and you turn up the external pressure. Okay, that was the idealized calculation. And in this study, these authors found indeed that when you turned up the external pressure, the growth rate was enhanced, and the wave number was reduced for instability. So things really did get much more complicated very rapidly. You made lots more star formation. So here's an intuitive way of seeing where this might come from, and that is that when I talked about star formation before, I basically was comparing a gravitational, an orbital velocity with which is represented by sigma. Okay? But now I'm replacing that by the velocity of some outflow from the central object, this radio cocoon maybe, which could be much faster. Okay? And that then gives me a way of accelerating star formation, making it more coherent and speeding things up. So that basically is the idea. And of course it's more complicated because once I make those stars, I'll make some supernovae, I'll get even more star formation. So if I can do the triggering, then things rapidly get more and more complicated. So does anything like this ever occur in nature? The answer is yes, it does. We have some beautiful examples. And this is the classic example of triggering. So near this radio galaxy, these are the radio contours, there is this wonderful blue object called Minkowski's object. Okay? And when the study was done using GALEX, they looked at the isochrones, and they found that this cloud was made of young stars, and even the age gradient was consistent with a shock wave compressing them and inducing star formation. This is the classical example of triggering of star formation on a galaxy scale. Here's another example, HST observations of Centaurus A, the jet in Centaurus A, show these regions along the jet of triggered star formation. And one more case, so this is a study of molecules, okay? And studies like this are about to be done in far more detail with ALMA, etc. This is from a few years ago, one of the early papers, and they noticed that along this radio jet, there were clumps of, massive clumps of CO, and this is redshift 4.7. So you need molecules to make the stars, so it could well be that the excess pressure, and I'll show you how that might work with the radio jet, is helping to pull that. So this is one example of early ALMA observations, showing again, this is just the beam, it's highly beam distorted, but nevertheless, you can see that there's a radio axis, there's axis of radio outflow, and there's a lot of molecular gas. And the idea here would be also to look at the excitation, higher level of CO, and see if there is an excitation connection with the radio gas. I'm not sure that question has been answered yet, but that's the sort of thing one can hope to do in the very near future. And that will give you a much more direct connection with the two. Okay, simulations suggest that this is not a crazy thing to do. So I want to show you examples of simulations now. So first of all, this is the work of Alex Wagner, who looks at a radio jet, black holes over here, going through a clumpy interstellar medium. And the jet rapidly gets unstable, and you get this cocoon of plasma, and hot plasma channels out through these gaps between these clouds as well. And here's a bow shock that expands into the surrounding medium. And so this is highly overpressured, full of synchrotron emitting electrons, and you can see the radio contours up here. And what Alex studied and his co-workers was the loading of the gas by the outflow and the production of very high velocity filaments. So he was getting velocities up to 1,000 kilometers a second of gas being trained even with the high velocities, the outparts, etc. And it is tempting to compare this with objects that we look at, such as, again, the poster child is probably Markarian 231, and again you can see evidence for the QSO and the jet axis and outflows with some indication the highest velocities are connected to those outflows. So it's sometimes you like to look at movies, so let me show you simulations, again from Wagner, of two different geometries for the clouds. So you're going to see the jet in the middle, and here's a disk-like geometry, and here's something more spheroidal. Okay, so first the disk, and then so you're going to see the outflow coming along, and again this is the bow shock that's forming ahead of it, and it's going to compress much of this gas in the disk, and in the more spheroidal case, much of this stuff is dispersed. Okay, so it's rather less effective, maybe. So this tells you it's not just cloud masses that come in, but the geometry is a critical factor in getting this right as well. Okay, so and here you will have regions of enhanced pressure. Now, could these regions of enhanced pressure actually form stars or not? So now let me turn to another set of simulations done by Volker Geibler. And again, these are 3D simulations, clumpy media. Here's a gas-rich disk. Here's the jet rapidly going unstable through this clumpy medium and driving this bow shock with very hot plasma behind it. So there's basically a working surface out here, and you're filling the stuff behind the surface so it breaks through with hot gas. Okay, so what I want to show you now are the pressure maps, the effect on what goes on in the disk. This is 5 kiloparsecs here. Okay, so this is okay. So first of all, let's show you that one again. So these are spectacular pictures. So you can see that the bow shock, behind the bow shock is enhanced pressure, which is going to feed back on this disk. You would expect to see very complex radio maps at the same time, perhaps with jet-like features. Though I should say that because of the geometry, it may not matter if it's jet or something with a wide opening angle. So here's the density map, and here's the pressure map. So this is your original disk, and you're going to watch the effect of the explosion on the pressure and on the density. And so the density, here's the bow shock, and you can see you're compressing the gas. So the gas disk is really being compressed significantly. This could lead to enhanced star formation. Or does it? So using very naive estimators for star formation in the literature, thresholds, this is what happens. These are the old stars existing there previously in this gas-rich disk. And the jet's going to come along and see an edge on, you see an injection of new stars. It's more dramatic, sorry, let me get that. It's more dramatic if I look at it from above. Wake this up. There's the old stars, and then the gas starts getting compressed and blown out in the center. So in this case, you get a ring or a shell of star formation. So and this is kiloparsecs across, so 5 kiloparsecs. This is the sort of signature that you might expect from positive feedback. Okay, so to try to convince you that this really does happen, I'm going to give you an example that's very close to home. So if this were to happen, then the stars that you make would be acquiring some significant velocity. Okay? Now, that you can look for in principle with modern techniques of integral field spectroscopy, with traces of different, that have some injection that's very much a radial component to the velocity distribution. That has not been done yet, but what we can do is look at the extrema, the very high velocity stars. And so the Milky Way is a great example where we know there are explosions in the center of order 50 million years ago. These are the famous filmy bubbles, gamma ray map. And these are high velocity stars. So this is the escape velocity. Okay? And there are many stars, and all of them are coming from, we've now got information on so many of these, are coming from the central region. Okay? So something's going to descend to eject stars. Now, there are different theories. There's never is a clean answer here. And probably the favorite theory is a binary black hole and stars interacting with that and being ejected, binary stars ejected with a binary. Something like some complex emergence. But it could be. And the reason I think that one has to take this more seriously is not just these stars coming from the center and are consistent with an explosion, a series of explosions 50, 100 million years ago, 10 million years ago, of that order, different episodes could have done this. But here's another amazing case, I think, where in the case of M87, so in the example I've showed you, we only have a 4 million solar mass black hole. Let's imagine we have a 100 times more massive black hole. You can get a much more impressive phenomenon. You can not just eject single stars, you can eject whole clusters of stars. So here is an amazing example. And to show you this field is developing so rapidly, this was just, I think, on the web, I don't know, maybe today or yesterday. But they found a globular cluster at a velocity way larger than escape velocity, and coming presumably from the central part of the cell. So again, the only theory is interaction with the central black hole, and everyone who's tried to model that would have a very hard time conserving a compact star system with that sort of interaction. So, I would think this is a prime example. And one more very curious case, again, our own galaxy close to home. So that our black hole has a gravitational influence radius of about 3 parsecs. Its gravity dominates there. Okay, and that is where maybe most of the damage will be done by initial outflow and overpressure if there were some gas supply. Now, for gas, there is evidence for disks of young stars. But there's also a nuclear star cluster, which is stretched along the disk at the center, and this is roughly the gravitational influence radius of the black hole. And so the early jet phenomenon, if it could have been, now, there is no simple explanation for things like this, but if this were in any way due to induced star formation, then having something, 3 or 5 parsecs in our galaxy makes you wonder whether this could not be important in the big galaxies with massive black holes on bulge type scales. Okay, so moving on, let me try to. I'm going to draw this talk to an end shortly, but I'm going to show you some observations first. Well, this is one issue that comes into this. I mentioned there's a whole cosmic history to this. When you go back in time, you'd like to know which came first. And so, for a long time, when we looked at the cosmic starfate history up to 2 years ago, this was the data. And when we looked at the black hole accretion rate on the same diagram, and we multiplied it by 1,000, which is roughly the ratio of black hole mass, spheroid mass to black hole mass, we got the red curve. And clearly, this suggested that, as you go back in time, the black hole feedback is totally irrelevant. Well, but the situation's completely changed in the past couple of years for 2 reasons. One is that we now have these very deep infrared observations, which tells us that we're missing a lot of these very luminous, mostly high redshift objects, and it's very hard to know how to correct for that. This is a very simple back-of-the-envelope estimate that might come up to there. But the other thing that pushes you in a similar direction from the star formation point of view is that there is new ways of correcting the dust extinction and for downsizing. You have to correct the rest frame luminosity function to get the solar star formation rate. When you put all those things in, the star formation rate comes down as well. So now the modern data says everything is in parallel. Okay? To redshifts as high as we can go 5 to 6, 30. This is the result of Beruzi, for example, which raises the star formation rate from this previously to this one. Okay. Right, so that's sort of the black hole story. I can't only talk about supermassive black holes, I have to just say a word or two about the smaller black holes, because some of us believe that the way that if you make the big ones, you should also make a lot of smaller ones, some intermediate mass black holes, which are probably were in dwarf galaxies, and may still be in them for all we know, no one has really proven the contrary, but many of those are stripped, so we should have an awful lot of black holes around. And those, during the reactive phase, might have done something. And so there are two baryon problems that we worry about, and this is a case of intermediate black holes to the rescue, okay? Perhaps, okay? So one of them is this curious baryon fraction problem. So here are the galaxies, okay, Milky Way being roughly over here, and we're seeing, only 40% of the baryon fraction that nucleus predicts. So those baryons have gone somewhere. We're pretty sure they're out there in the intergalactic medium. There are evidence beginning to point that direction, but how did they get there? So we don't really know. Supernovae in the Milky Way almost certainly cannot do the job. But what could do the job are at an early stage of galactic assembly, if there were lots of smaller black holes around, as some theories suggest, they would do their thing in the smaller galaxies and give you additional ways of. And at the same time, there is what has been called the too big to fail problem. The more massive dwarfs are predicted by the simulations, and the grey stuff is where we see things, this is where we don't. And again, adding black holes of intermediate mass in the dwarfs, magnetic type dwarfs, would be a way of resolving this. And again, there are, these are theories from McDowell and collaborators, which show his predicted distribution of intermediate mass black holes. This is the central kiloparsec of the galaxy, 5 kiloparsecs, lots of them around. But the total mass is trivial. The sum of the masses of all these black holes is equal to the central one. I mean, that's the basic rule. So you're not doing any dramatic things to the total black hole budget in the universe, but these are the building blocks in principle of the big ones, or could be. But they're the relics of those building blocks, because obviously you've made this with several smaller ones, but many of these will be left behind. That's basically the theory, that there should be roughly the same mass left behind, and if so, it leads to solutions to these sorts of problems. Here's an example of how you reduce the baryon fraction by putting in this intermediate. Okay, summary. So I think it's fair to say that we don't understand star formation in extreme conditions. Okay, that we are beginning to have a good grip in the Milky Way. In the other galaxies, we can resolve star formation, but far away, I think we have to speculate. Likewise, to black hole formation. And so the basic question you have to ask: is it the same as usual far away? That is it just the gas conditions are different? Much more gas in the early universe? Is that all that's going on, or is there something new along the ATM connection? So I want to try to persuade you that we have to be open to new ideas. Okay, that's really my message. And I'm going to just end by showing you a series of slides that first begin with surprises in galaxy formation over the past few years, some of which we understand, others which we don't understand, but with hindsight. And then, stuff that relates more positively. So here is, I think, a classic example of something that was totally unexpected from observations, and the theory at the time had no way of handling this whatsoever. And that was what we now call downsizing, the fact that at high redshift big galaxies were in place first, and not were they just in place first, but they had, because the age of the universe was younger then, they had a shorter star formation time. Whereas hierarchical theory says the big ones form later, and the age of the universe is longer, so they're 3-4 times longer. So exactly the opposite should happen. So this was, and the way one can do this is you can use the alpha element as a chronometer, and that basically gives you the ages, because again the oxygen and magnesium is formed by the type 2 supernova at a short time scale, the 1A is formed by iron, and so the ratio measures, and the fact the ratio is enhanced in the big galaxies tells you they formed those short time scales. So not only do you look back in redshift, but you also get the time scale from chemistry. So that's very powerful, and the modern observations, is beautifully showing how downsizing works in recent Herschel studies. So as you go to higher redshift, this is how the luminosity function changes. Sure, you see fewer galaxies, but if you look at the massive ones, you see vastly more massive galaxies. Okay, so they're in place. This is the must be there in place radar. Okay, so that's one example. Here's another one. You know, active nuclei, the quasars, both radio loud, radio quiet, more radio loud as I'll demonstrate in a second, have enhanced star formation. This is what you would get with if you didn't have the star formation, and you find the star formation is more than you know, some part of this infrared luminosity may be AGN produced, but it's believed that star formation is enhanced. Now, this is a very vague way to look at it. Let me be a little more direct, first of all. You know, that's an issue that I think we have to understand. The connection is something that's not understood. Here's something else that I think is a little bit disconcerting. So this is the star formation time scale, the inverse of it. This is m star dot over m star. That's what this is, an inverse time scale. And here's the Milky Way over here somewhere. You know, it's a very long time scale. You know, 50 rotation times to turn to gas stars, whatever. Okay. And as you go back in redshift, this inverse time scale, the rate gets higher and higher. For making stars. The time gets shorter and shorter. And so when you go back to redshift 5 or 6, there are limits, and we don't really know whether it keeps on going. But it's already 100 times different from the local one. So again, you ask the question, is this something very different, or is it more of the same? And this high star formation rate correlates with nuclear, with the AGN. This is the connection. When you look at this inverse time scale, you find that AGN, dominate, okay, where it gets higher. Again, this is just the low range of the universe. You have a handle on this, and this is the way this goes. If you try doing the imaging, then there are two intriguing things that come out. This was the data I showed you before, where you saw the massive clumps in galaxies. Now, in some cases, with radio AGN, so you can see these massive clumps of star formation often have our AGN associated. So that seems to be intriguing, and there's even some morphological connection. Here's another example of a nearby active galaxy, not too far away, with redshift 2, again with this incredible few kiloparsec ring of star formation. Again, maybe this is aging, maybe it's not, but this is the sort of thing one has to watch out for. And finally, these incredibly high star formation rates. Here's an example of how you can specify this, the surface density of star formation. This is as you go from Milky Way type values over here to those extreme cases we know, you're up by many factors of 10 in star formation per unit density, and the turbulence is going up as well. So these are the extreme star forming objects. And again, you ask the question, is the physics the same here as over here? Again, I think the jury is out on that one, I would say. And then, so here's one more extreme worry that we have, again, observationally. Now we can measure gas outflows. We see incredible gas outflows at high redshift. And, for some cases, the outflows are, 200 billion years, that's fine, maybe. You can supply gas at those timescales. But look up here, for the most luminous objects, the gas depletion time is only 20 million years. Enormous star formation rates. So again, is this negative feedback driven by the AGN, pushing these are AGN, or is something being enhanced before it's driven out to get to star formation? Again, we simply don't know. Here's again something which I find fascinating. Very new observation. Again, this I think I took off the web today, actually. So this is a study of the nuclei of galaxies as you go back in redshift. And what is amazing is you see these dense cores in quiescent galaxies. And as and today, there are a few percent or something. As you go back in redshift, they're 10 or 20%. And this is so you compare the dense core with the rest of the star formation, and they really are relatively dominant at high redshift. And so these are the sizes of the cores, and this shows you in the sample in this redshift range that one has these very dense cores, which are a significant fraction of the mass. Meaning, when an intense star formation in small regions at high redshift. That's the message behind this. And again, this was not predicted by any model of star formation yet. Okay? I'm sure the theorists will arrive coming up to this eventually. Okay, so those are my surprise things. So let me end with why I think positive feedback is a possible answer, why something new is needed. So, and I'm just going to show you some recent examples. So here is one of them. In several giant radio galaxies, 4C galaxies, that's redshift 3 or 4, in this case beyond 4, with detailed spectral analysis, including Herschel data, one can uncover a young population. So here is the old population, a little bit less than the age of the universe at that epoch, okay? And here is this young population, 30 million years old, in a radio galaxy, with roughly the same mass as the old population. So that is, again, something pretty amazing. A starburst in a radio galaxy, and that seems to be a common phenomenon. And this is one example of that. In this data set, the authors, William Drouin and collaborators, have now extended their sample to include a dozen or so 4C radio galaxies, and they find that if I look at the specific star formation rate, it's enhanced. So the stars are radio galaxy detection. So when you see radio emission, you seem to see even more rapid star formation. This is the inverse timescale of star formation. Shorter and shorter as you go back in time, reaching 4 and 5. Okay, so the radio phenomenon is playing a role, okay, suggesting there is a connection. Here's another intriguing example, again, another survey, an independent survey of radio galaxies compared with X-ray AGN. And again, they're comparing, as a function of X-ray luminosity, objects which have certain star formation rates. And when you look at with the radio, you just find you just find enhanced star formation rates basically, compared to where there's no radio access in terms of star formation rate. Again, it's circumstantial evidence at this point, but I think it's telling us something. Okay, so another study, again, this evidence just simply won't go away. This, I think, was taken from the web today as well. Okay, so a study by Fuso et al. When they look at a series of, this is the disadvantage of having the FRL week, about ample time to search the web and find new examples. And I'm just making the point that every day we're getting these amazing new examples. This is an incredible example of, I think, positive feedback. So what they're finding, again, is that they compare the star formation rate, okay, as a function of optical luminosity, including AGN luminosity, again, radio loud versus radio quiet. Again, for the lower mass AGN, there's an enhancement of star formation, okay, suggesting that there is some incredible things going on. The final example I'm going to show you is not published, and this, to me, is the most impressive thing of all. So what Peter Bartel, the students and collaborators have done, is they've measured the sizes of these radio globes, okay, in this sample of giant 4C galaxies, many of which have a star formation, okay? So the size of the lobe gives you a time scale. So now we can compare a time scale of star formation, okay? And so this is a length scale, okay? And this is star formation. Okay, and the amazing thing is that if you had negative feedback, then surely you'd see evidence of quenching. But as you were close in, you'd see less star formation. But again, it's hard to tell from this, but the general trend is the opposite, okay? Depending whether you look at quasars, radio quiet objects, which from the shock point of view are much the same as the radio loud ones. Everything gives you sort of quasi-spherical shocks in the air. The star formation rate, the further out you go, the longer the time scale is going down. So that to me suggests that. Anyway. So again, summary slide, I showed you the evidence for star formation rate, black hole accretion rate. They seem to be parallel each other. This is 1,000th of this. That is this the tail wagging the dog, or the dog just shaking its tail? Is one influencing the other, or is it some external event like a merger that's producing both? I think the jury is really out on this. We don't know, but the fact that they're empirically parallel is very intriguing. It means, I think, that you really have to include the AGN in your massive black holes and the story of galaxy action. Now, the weakest point in all this is the formation of the supermassive black holes. So this is a problem that's been studied for a very long time, and the pioneer in this field is Martin Rees. Okay? So this is a famous diagram that he produced in 1978. Okay? So it shows you two different channels, basically gas dissipation, very high accretion rates. You don't have, typically you suppress the molecular cooling, that's the modern view of this, but it's the same idea. You have runaway gas accretion, you vacuum make a central massive object, or you have collisions of many stars with seeds and leading. So this was how it was in '78. The most recent review I could find, by Rich Bigelman, is beautiful. The color graphics are amazing, but the story is exactly the same. So theory has not advanced one iota, in my opinion, in this time scale, and that's because it's a very complicated problem. So but that's the weakest link in this whole theory. Okay. So, thank you. I will stop here. Right, I think, that's a problem to be studied. It's hard to get that much gas, in there just by accretion, but the time scale is just too slow. So getting it from far out just takes too long. So maybe it means the gas was there already, and you trigger it somehow. That would be, the gas certainly was there at the beginning before you made the stars. So that's one likely possibility. It's a dense core. Again, you have to look at these relative timescales to try and get there. So the trick is getting the timescales. And so with the AGN, we now finally may have some clue from radio lobe sizes. Another whole issue might be duty cycles. I mean, there is ways to get independent of the stellar timescales. Usually by comparing those, we'll get some better idea. Plus the morphology, what really is done.
Any other questions? So I do have one. I mean, if you go to Redshift 2 or so, most galaxies are rapidly starting, almost all. Super lower mass. But the number density of AGN is way below the number density of L-star galaxies. So even if some AGN are doing, probably most galaxies don't have
So, well, so two comments. First of all, there's a huge population of quiescent galaxies, Redshift 2 recently discovered. So definitely by no means illegal stuff. And those quiescent ones are dense cores that form much earlier. And then the AGN duty cycle is very different from the sulfation duty cycle. So it may well be that if that duty cycle is not as long, time is not as long as you think it is, if the AGN lights up a shorter burst, that will reduce the numbers. And so we really don't know. If the sort of thing I'm talking about were true, then the duty cycles would, both starvation and AGN will both be very short, and that would affect the numbers one is measuring. So unless you understand duty cycles, it's really hard to go from simple counting to deciding what the influence is of one or the other.
Well, what I would say is, this we don't have great information on. If you look at the CO, for example, try to estimate the gas mass, and this is just stardust. In the galaxies where you see CO, you always see stardust. And it looks like it sits on the edge.
So that's not even true. Okay, so there are cases now being found. Again, it depends on how I think we're very biased. Right? We're biased by looking at star formation and looking at CO. But there are cases now which are very, very puzzling. You find massive CO clouds known at star formation at high redshift galaxies. So we have the slightest idea what's going on. But all that tells you is that we don't really understand.
Let me project you back to things that haven't been understood, at least back to Greece. I mean, actually, probably associated with that. But I know that you've thought about it a lot, and you must be integrating this into the story, which is the issue of going from first stars in tiny objects up to the stage where we're starting to get much more massive entities. So what's your picture now? Or is it purposely fuzzy along the lines of complex diagrams because there's so many branching?
Well, look, star formation should be immensely easier than black hole formation. It should be, okay? if you look at this, clearly it is. On the other hand, we're a long way from understanding it, I would say. Even in the local Milky Way, you can ask questions about, you know, starless clouds being supported by turbulence, what's the origin of turbulence, why is the center of our galaxy not forming stars that effectively, you know, way below the Schmidt-Kennicott relation if you look at local regions. I mean, the diagram I showed you from Krumholtz was totally misleading, actually, because there are many clouds that don't lie in that diagram that they didn't plot. Okay? So
you're saying ignorance now, therefore triple ignorance back then. But okay, so let's try something else. What do you think the IMF is at redshift 10?
Listen, I'm perfectly open to any suggestions. Okay? I think there is no observational evidence that you can believe that's credible that says it's any different in any nearby galaxies, including the ones that Charlie Conroy and company look at, the ellipticals, the massive ellipticals. All of that has huge question marks because of various, you know, empirical issues, phenomenal issues. So there's no reason to think it's different today in different environments. And as far as very high redshift, well, for the first stars, it's clear that we weren't making, you know, then it was different, there's no question. Otherwise, we'd have this immense, you know, G-dwarf problem, etc. So you know it has changed. So at high redshift, you have a lot more freedom. And you're driven to that from chemistry, from realizing the universe, all sorts of reasons to push it to changing the IMF. If you're actually got a theoretical reason for why that is, I think we're still a long way to go.
Can you comment on H1 dwarf galaxies and its implications for the Big Bang?
Okay, you mean the presence of H1 in some dwarf galaxies? Well, it's going to form in and eventually make stars, I suppose, and we do suddenly have gas-rich star-forming dwarf galaxies. There are episodes of star formation, and eventually when you make some stars, then you blow the gas out.
Sure.
So you have these multiple, and we see multiple episodes, that's for sure.
But I mean, speaking more specifically about claims that, in fact, a lot of gas hasn't been blown out, it's being stored in the form of gravitationally stable H.
Molecular H, even very compact. That's one theory, that it's stored some. It turns out that if you want to store the missing gas, you'd better put it in some very bizarre form. And so the most bizarre form, which foreign source comms and company failure bring papers on, is to force yourself to make it very compact using mass cold, which is completely crazy. I think. You know, I think it's very hard to store enough gas. Where the gas most likely is where we begin to see it now with the studies of circulating galactic gas. So there are claims which I don't fully believe, but based on COS data, that one is seeing, you know, some large fraction of the missing baryons now with intergalactic absorption, some conventionally ionized important parts. So it may well be that how it got there is the question. Why is it there? Why is it even enriched? If it's enriched, it must have come from something. Must have come from the galaxy. So it's gone out, but how did it get out? That's the big question.